The problem with what we have just seen is that if there are lots of objects which are not garbage, then because part of the garbage collection process is a stop the world event, our application is paused while the marking phase runs, then the users of our application will probably notice that our application has frozen, perhaps for a few seconds at a time. This wouldn't be acceptable, so to avoid this, we actually have something called generational garbage collection. The starting point for understanding generational GC is that most objects in Java live for a very short period of time. If an object survives one garbage collection, then it's more likely to live forever. We need to remember that it's faster to run the garbage collection process when there's a lot of garbage, or when there's only a few objects that are going to survive. So to make the process as efficient as possible, the heap is actually organized into separate sections, and this is known as generational garbage collection. So the heap is divided into two sections. One is called the young generation and one is called the old generation. The young generation is typically much smaller than the amount of space I've allocated it on screen here, but this can be tuned, as we'll see later on. And actually the young generation is split into a further 3 separate sections, and we'll look at that in just a moment. But the idea of the young versus old split is that new objects are created in the young generation space. The young generation space will fill up quite quickly as it's small, and when it's full, a garbage collection takes place, but only on the young generation. Because most objects don't survive for long, the young generation, which is full of new objects, is probably mostly garbage, so the process to garbage collect the young generation should be very quick. There are very few objects which need to be marked, and it's small anyway, so it should take fractions of a second. We'll not notice the application freezing while this process takes place. Any surviving objects are then moved to the old generation. The young generation is now empty, and any new objects can again get added to the young generation. The garbage collection of the young generation is known as a minor collection. So as your application runs, there'll be lots of minor garbage collections taking place, and they'll be pretty much instantaneous because the young generation will be quite small and mostly full of garbage. So I hope you see that this is now a much more efficient process than what I was first describing. In fact, most of the time, the garbage collection never looks at the entire heap, but rather just at one small part of it, the young generation. Now, garbage collection will also run on the old generation, but only if it's needed, for example, if it gets full. This is called a major collection. A major collection will be a lot slower, as it's a much bigger block of memory to sweep, and there may be many objects in the old generation that are still alive, so the marking process will take longer. And of course the compacting process, moving all the surviving objects into a single contiguous part of the memory, that will take some time also. Although, as we'll see in the next chapter, in the most modern garbage collectors, even this has been made really efficient. But in theory at least, a major collection could take a few seconds rather than the fractions of a second that we see in the young generation. But hopefully this all makes sense and sounds quite efficient. We have lots of very quick young generations collections happening, but if we really need it, we will have a collection on the old generation, and that might give a noticeable impact on the performance for the user. It might pause the application for a few seconds, but the minor collections certainly will have no noticeable impact.